Hmm. My voice is fine. Let's quickly talk about today's contest solutions. So, first one was very easy. You just have to reverse the integer that is given and return the absolute difference. So, what I did, just convert this into string, reverse the string, convert this string into integer, and return the absolute difference. Very simple, very easy problem. So, yeah. Now, next one. So, here you have to remove some characters, right, in such a way that the rest of the characters are same, right? uh Possibly none, and it should be non-empty, right? This is a very important property that we're going to use. So the thing is, you can make this whole string. Let's copy this and see. So we can convert this to like AAAA, either B or either C, because all the characters inside this should be the same. So to make it something like this, AAA, you need to remove this B and C. Now, if you're removing any element, you will need to add the cost of that particular index, right? So the cost is going to be the index of B3 plus 10. So the cost of this operation is actually 13. Similarly, if you'll make this B, then the cost is going to be, the sum of all these 1 plus 2, 4 plus 1 plus 10. 3, you got 8 and 18. The cost is 18, which is actually greater than the previous answer. So this is not better. Now for C, the cost is going to be sum of these. So it is 5, 8, and 11, which is the minimum cost that we are getting from all these operations. Now, one thing to notice is that this S, it only consists of lowercase English letters. So the idea is you can iterate over all these letters, right? So here, if I is 0, the character is A. If I is 1, it will be V. Similarly, if I is 25, the character will be Z. So just loop through all the possible character, and this is basically the character that you are trying to convert this string into, right? So if I is 0, then you're trying to make this string as AA, something like this. So all the values that are not equal to this character, you're going to add their cost. So to make it like convert this string into this, you're going to remove this B and C. So just adding a cost, and I'm just keeping track what is the lowest cost. And this thing here that can be non-empty. So it is actually an important property, because does that even make any? Okay, so cost is actually positive. So I don't think it is that much useful, but yeah, the idea is, if you're going for like some other character that is not in this string, for example D, then you will have to remove all of these, right? So cost is only going to increase. So we will not have to handle those cases where the latter is simply not inside the string, because the cost is always going to be greater. So that is not required. So yeah, simple solution. And let's move to the next one. This was a good problem, because uh, you need to take your copy and a pen and try to see the pattern. So first of all, first thing to realize here, if you have a 1 here, this is not a good example. Okay, let's quickly take an example. Let's say you have something like this. So this 1, it is actually coming 2 times. So frequency of this 1 is actually 2. Now the thing is, apart from this one, the frequency of other letters should be greater than this, right? So if, because if that is not the case, I mean greater than or equal to, so if this is not the case, then you simply cannot make these two things unique, right? Because you don't have those enough elements. And this whole operation is what I'm just doing. I'm just checking this particular thing, right? So count is storing the count of the value inside nums, and this is storing the count of the values that are coming inside the forbidden. And then I am just iterating over it, right? And if the count, right, if for example this one is coming 2 times, so if this is greater than n minus this n minus this, there are total 3 elements, and this is coming only once, that means there are 2 other elements that are not 1. So this is the logic, right? So it should so it should not be greater than these 2 uh, unique characters. So now if you can actually make it, what is going to be the minimum swaps, right? So think of it like in a single swap, right, what you can do, you can change the position of 2 characters, right? So for example, let's take something, let's say 1 and 2, and in a forbidden it is giving like 2 and 1, let's say, right? So in a single swap you have changed these 2 positions, these will be equal, right? Yeah, let's say this is also 1 and 2. So you can change the positions, and now the condition satisfies, right? Now it is not equal to forbidden. But there is actually a edge case. What if you have like kind of something like something like this, so this is coming twice and this is not going to work. So if you have something like this where one is coming twice, then swapping these 2 numbers actually doesn't do anything, right? Now this this EQ is basically the number of elements that are actually equal. So these are the elements that I need to change. So the minimum number of swap in the optimal situation is just the seal value, right? Seal value of this, because these many swaps you need. But if you have these kind of cases, then there might be a situation where you have like a element repeating, let's say 5 times, right? So to change the position of those elements, you need to make at least 5 swaps. So if you have something like this, let's say 1122, you need to swap this 1 with this 2. Similarly, swap this 1 with this 2. So you need at least 2 of those. So while returning the answer, I'm returning first of all the swaps in optimal condition. And if there is a repetition, then I'm repeating like the maximum frequency. So yeah, maximum frequency is just the maximum time this value is coming. That is nothing but the frequency. Okay, that was it. And see, in this scenario, the output is -1 because this 7 is coming twice, and there is only one element, unique element, that is not 7. So it is not possible to convert this. Similarly, This is already unique, so we don't have to do anything, right? So basically, this EQ is actually 0. So we are just returning 0 from here. Okay. Okay, this was actually a bit difficult, I would say. The only reason I was able to solve this because I have solved similar problems. Um, so all of these problems, they are actually based on a concept, which is a DFS tree. So this is like a amazing blog if you want to learn about things like, things like, first of all, DFS tree, if you know this concept, if you know how the tree is traversed and how you can perform operations into it, you can solve a lot of problems in like big O of an optimization problem. So yeah, especially the dynamic programming problems where you have to keep track of some values, right? Rerouting DP kind of problems. Or there is also one more type like in out DP, which is nothing but rerouting. Yeah, there is also things like you can do articulation points and things like bridges, right, in graphs. So by just this technique, DFS tree technique, you can find all of these things, back edges, things like that, right? Span edges. So I believe this is actually one of a good technique in data structure. So yeah, should definitely go and check it out. So after you're aware of this problem was about like a single technique that you have to realize, which is this thing. And I will explain this. I will try to do a better job. Okay, so first of all, just go through the statement, read the problem, and then come back. And yeah, so how I thought about this problem. So let's take any edge. Let's take this edge. So what will be the contribution of this edge, right? So let's say the element below this edge, right? So there are three elements basically, actually four elements, this as well, right? And these are the group numbers of these elements, right? So we have one element of group 1 and two elements of group 0, these two, and one element of group 2, right? Now above this tree, in this whole tree, right, how many elements do we have? Let's take an example for this first group, right? We have 1, 2, 3, 4, and 5. We have 5 elements. So how many pairs you can make, right? So there is only one element here. You can only form pairs like in one. So for example, this one and this one, you can form this one, this one, this one, this one. So ultimately, the pairs, number of pairs is going to be the number of elements outside the subtree of the same group and the number of elements in this subtree uh, of the same group. So it is just going to be 5 into 1. So if you have, let's say, two elements, two elements of group 1, then the answer is going to be 10 because now every single element can form two pairs, right? So the contribution of this edge is actually going to be the total edges, right? So the total number of edges, nodes of this group minus the total number of nodes of the same group in this subtree, which is 2, right? Multiplied by the total number of nodes in this subtree, which is 2, right? So this 2 is basically number of nodes in this, and this is basically giving you the number of nodes outside this subtree. So this is exactly what is happening here. So this group is already given. So this is basically a particular node belongs to which group. And this total is like the total number of nodes in a group. So yeah, this is something called coordinate compression. It is a very common technique, especially in RMQs like segment tree, Fenwick tree. In problems like inversions, we use this trick. So I have just compressed the coordinates for group. For example, here group is like 1, 1, 1. So I have compressed it to like 0, 0, 0, something like this. If you have like, see, there are only two unique values, 3 and 2. So I made this 2, or like made this 3 as 0 and this 2 as 1. So it's 0, 1, 0, something like this. It doesn't change the answer, but yeah. So here I'm doing the same thing as I explained here by this. This count is storing actually for any subtree, this node, and how many values are there for some specific group, right? This is what this count is storing, and answer is getting stored into this. So yeah, just adding up the contribution of every single edge. This I believe is very important to optimize this problem, because this has to be solved in n log n. So this was one of the important. So what I'm doing, I'm just traversing through, for example, for this node, I'm traversing through all the childs. For example, this one. I'm picking the child which has the largest size, for example, this one, and I'm just putting it to this, right? Then what I'm doing, I'm traversing through all these edges, all these child nodes again, and adding it. That's it, right? And again, I'm skipping this node because I have already added it. So it's a little bit optimization that I did. I think rest of the thing are fine. This is basically the addition of node. Like, so what we are doing, we are just adding this thing right into this parent, the contribution of whole subtrees, but we will also need to add this particular node. So how am I doing this? Is basically I need to find what is the group of this node and just add it, simple as that. So yeah, I think if you know this thing, like how you can traverse a DFS tree and how it represents the values, this particular problem was not hard. Ankush Kumar, please help. What kind of help you need? What? Yeah. So that this was the problem. Coordinate compression, and here I'm storing how many nodes, total nodes exist for some specific group, so that I can use it here while I'm subtracting, right? This total, that is it, I believe. Yeah, I'm ending the stream.